But we're seeing this transition over time to a larger number of commercial and international organizations that are joining in with U.S. government organizations in developing space systems. And so the more of these capabilities that are developed and deployed, the more we are evolving into a space ecosystem environment. That brings up the challenges of integration within those different organizations, and also the need for essentially doing do no harm analysis.
Hello, welcome to the Space Policy Show. We're now celebrating our 5th year, and I'm Colleen Stover with the Center for Space Policy and Strategy, part of the Aerospace Corporation. I had the chance to attend the Goddard Space Science Symposium outside of Washington, D.C. recently. It's in its 62nd year, and the symposium brings together scientists and engineers and leaders from across the civil space sector. From NASA to NOAA, from lunar landings to deep space habitable worlds, the fundamental science and technology that space provides was on display at the symposium. But also the competition for leadership in space, both across industry and across nations. Today's show discusses the integration of science and commercial goals through government-sponsored programs like NASA's CLPS, recent successes, and what the future looks like. I interviewed Firefly Aerospace and Intuitive Machines, the first U.S. presence on the moon since Apollo, with their commercial landers paid for through the government's CLPS programs, the Commercial Lunar Payload Services Program. And then we shift gears in the show, and we talk to the Chief of Space Policy at the Planetary Society. That's the one with Bill Nye the Science Guy as the CEO. We talk about how to align science and industry needs. And then finally, we meet with leaders and hosts of the symposium from the American Astronautical Society, closing out some of their key takeaways from the panels and discussions. Oh, and we even hear from students that attended the event. So thank you for joining. And if you enjoyed today's show and you want to learn more about our deeper research across the space enterprise, go to csps.aerospace.org. Let's get started. Okay, so I'm here with Jordi Paredes Garcia. He is the corporate chief engineer of Firefly Aerospace. Thank you very much for joining me today at the symposium.
Yeah, very excited to be here.
So I wanted to, of course, congratulate you. Firefly stuck the landing.
Yeah, the whole team stuck the landing. It was a massive achievement for us and for the whole humanity. So we're very excited to be the first commercial company to fully stuck the landing vertically and softly. Yep. Very happy.
Well, tell us about the Blue Ghost mission then. Tell us a little bit about what was on there and what you had hoped to accomplish.
Yeah, so Blue Ghost mission had 10 NASA payloads. This was a CLPS mission that we started about 4 years ago, proposing, developing, and flying. And we launched, I think it was January 15th. So we lasted about 60 days from start to finish, and that included about 45 days to get to the moon.
This is kind of a transfer orbit that you were in.
Yeah,
right?
So what we did is we tried to go slow and learn about the spacecraft while we were going to the moon. So we first got lifted up by a Falcon 9, very happy with SpaceX and the service they provided. And then we spent some time orbiting Earth, trying out our systems, doing some fires, adjusting our orbits, understanding better the spacecraft, the propulsion system. Those are all new propulsion systems that we had developed internally with a main engine that we had acquired. So it took us a little bit of time to learn, but that's kind of what we designed the mission for. Spend 25 days going around, and then when you're happy with your software, with your performance, go to the moon, right? Okay. And that's when we decided to actually make the transfer to the moon and then get into lunar orbit. Then we spent some days also going around the moon before we would commit to do the final descent. And that's what we did about 15 days no, I'm getting the days wrong. But yeah, very recently on March 2nd, we finally landed and we did the final maneuvers and everything worked nominally and perfectly. And I'm sure you've seen all those videos.
Oh, it's so exciting, yeah.
Yes, we had never had this sort of like high definition video ever. So we're very happy to see how all our software and models had worked and how we were able to actually stick the landing and then have data and learn from that.
Right, so you were kind of gathering data for 14 days.
Yes.
Which is a lunar day, a single lunar day.
Correct.
In today's panel discussion, you had talked about the kind of thermal surprise that you had. So tell us about that.
Yeah, that was an interesting thing. As you can imagine, we spent years analyzing and modeling everything. Even when we were in space, we were correlating our models. And one of them was thermal, right? We landed on the moon, and as you said, we have about 14 days of lunar day, 14 days of lunar night, right? So this mission was only based to survive the first 14 days of lunar day. It was not based on doing anything after that because it gets very cold. But when we landed, we started seeing temperature responses that were a little bit like out of the ordinary. They were not expected. They were not matching. And we thought, like, we have the data, we have the models. We've done this for years. We understand with other vehicles. So what's going on here? Actually, after studying, we realized that there was some reflection that we're having from a crater, that heat was actually reflecting back to the spacecraft, to our lander, that we had not predicted.
Right. So you knew about the reflection, but just not the actual heat part of it.
Yeah, we didn't expect there was going to be so much heat getting into it reflected from the crater. Right, so that unknown that was unexpected made us, do some troubleshooting and decide, okay, what do we do? Which components of the vehicle we have to like turn on or off, and how do we manage that excess heat that we did not plan for? And the beauty is that then we added that into our thermal models, and it was like, oh yeah, here you go. There it is, right? Now, so now we have the models. Now we understand perfectly how that temperature works. And the team had to work very carefully on like, okay, I'm turning this on, I'm emitting heat here, I'm turning this off, I'm turning this off, to make sure all components were still survive. Right. Fortunately, the team was able to like maintain that. And again, the lunar noon only happens like center like 7 days when you get very hot. So that was like 2-3 days of like excitement on temperature. The rest of the time was good. But yeah, for reference, we were getting up to like, you could get up to like 230 Fahrenheit. Right, but we had also an eclipse later on that you can get to like minus 275 Fahrenheit. So like one of the challenges we had was like this: how do we manage all of the instruments and all of the components to stay healthy at these 500-degree range that you can have from the hottest that we've seen to the coldest that you see? Yeah. So that's one that we're happy that things worked out and nothing broke, nothing got damaged. But we learned from that, and then that's what we're going to put now for Blue Ghost Mission 2, Blue Ghost Mission 3, to ensure that they have a higher chance of success and we don't get bitten by anything.
Right. Well, and it wasn't just you guys that learned from it, right? Yeah. You've actually helped the entire space industry, like in terms of lunar landing. This is the lesson learned that can be shared.
Exactly. And that's what we're going to do. We want to help here, like all our partners and competitors, to actually learn, get to the moon, because we just need a heavier presence on the moon, right? And the moon to then be the gateway to go to Mars. So all of these lessons learned, then all that data is then shared. The NASA are going to be sharing all of those different science papers that are going to be coming out, and all that. We had like, it was like 110 gigabytes of data downloaded, and like 50 something gigabytes of that data was just science based. So all of that is now gonna be fed through the science community, and then help us understand better like how to get to the moon, how to operate on the moon, and how do we improve for landers, but also for like all of like the human exploration that we plan with the Artemis missions.
Right. So I mean, getting to the moon is hard enough, but we've done that before. But as you're saying, staying on the moon, kind of that continued presence through very hot, very cold, that's kind of what we're challenged with now. But there were 10 experiments, all from NASA, aboard your.
There were
lander.
Different NASA. We had some from Honeybee. We had other places, but yeah, most of it, they were all like NASA managed. And then when we were flying, we were getting all that data while we were orbiting, right, as well as when we were getting there, like trying to understand better the GPS signal. How does the guidance navigation system that we get all the way there, do you get signal going to the moon? Like studying soil interaction, studying like heat. Like there were so many science projects that they had, and we were just the ride, right? And then we got the data, but now it's up to the scientists to do all this and analyze and then crunch through all these data and tell us what we learned from that.
And the fact that NASA, will basically, as you said, kind of share that with the wider community, and we could just keep learning time over time. So I also wanted to ask you a little bit more about the launch at Firefly. Can you talk to us? You've got a rocket called Alpha going to, and then you've got the orbiter Electra.
Yes.
So tell us about the kind of rocket.
So we have two rockets. We have Alpha, which is our 1-ton rocket, and we have MLV, which is the medium launch vehicle. Still working on a cooler name, but
thanks.
It's 16 and so tons to low Earth orbit. Right, so like Alpha was our fully carbon composite rocket that we launched from Vandenberg.
It's a fully what?
It's fully carbon composite.
Okay.
So like the structure is not metallic like many of the rockets. It's a fully carbon composite that we build in-house. So it's very interesting. It's more efficient performance-wise. And actually that's the same kind of structures that we use for Alpha, MLV, for Elytra, our spacecraft, and Blue Ghost. A lot of the structures are based on our carbon composite manufacturing.
Okay.
So, and we share a lot of items. Like Alpha, we launched our first rocket in 2021. Again, unfortunately,
and you launched from where?
From Vandenberg.
Okay.
We launched from Vandenberg, and that's also like a shared resource. We have other launch providers that launch from there, SpaceX, ULA, which is a great pad. But again, it's getting congested, right, with a bunch of launches that we have.
All of the spaceports are getting congested nowadays,
they are.
The government ones,
Yeah, so that's why we have a port on Vandenberg. We've launched 5 rockets from there right now. Flight 1 that failed after 14 kilometers height, we had an issue. We corrected that. Again, it was the first time, so we learned. And then flight 2, 3, 4, 5, they were all great successes. And now we're about to launch flight 6, hopefully coming up next week. Still nailing down the date with the range, with all those resources. But yeah, it should be very exciting.
Cool. And so what's unique about Firefly rockets as opposed to you just catching a ride on a Falcon?
Well, so the beauty of an Alpha, for example, is a dedicated 1-ton rocket. We have many customers that we call it like, for a 1-ton spacecraft, you can take the bus or you can take the car, right? So some people like to take the bus because it might be more affordable, but it doesn't take you everywhere, right? Some people say like, I prefer to maybe pay a little more, but per kilogram, but I take my ride and I go where I want, when I want it, right? So like that's why, for example, in 2023, we did this Victus Nox mission that was launched in 24 hours. Right, so the Space Force wanted to show what if there's an issue and we actually have to get to orbit right away. What do you mean right away? It's like, no, right away, right? So we had this demo, it actually was not a demo, it was an actual mission that we got a call and said in 24 hours you need to launch a rocket, right? And then we had to go get the payload, enclose it on the fairing, roll it out to the pad, put it on the vehicle, put it vertical and launch it. On a small vehicle like ours, again, it's like 100 full tall roughly, right? 1 ton to orbit. We can do that, and we did it in 24 hours. The previous record had been 21 days. So we smashed that record from 21 days to 24 hours. Yeah. And that's one that DoD and even customers, like commercial customers, have been asking us, like, oh, can we do this rapid launch? Yeah. Like many...
The responsive launch,
Responsive launch,
yeah.
Yes. That's been crucial because sometimes you need it, right? You have a satellite that breaks, a satellite that gets damaged for some reason, and you got to replace it. Historically, we had spares to go up there, right? Yeah. If you know you're going to have a GPS constellation, you want a spare in case one fails, right? With our case, we can actually replenish. Instead of having it in orbit, waiting 15 years for the other one to break, we can have it on our facility, right? Or you can be ready, and then whenever that breaks, it's like, hey, here's your satellite, launch next, and then you can go and replace it. So that was very unique for our rocket. And again, it's a dedicated 1-ton rocket. It's the only currently flying 1-ton rocket commercial in the world.
So let me finish off with a question for you. What do you think government could do better to better integrate commercial into government programs and to kind of share, risk, cost, etc.?
Yeah, I gotta say, one of the challenges is to like make these missions under this tight budget, right? And then it's always a compromise between tight budget and reliability, redundancy. We're always playing that fine line that not just us, but all of the players trying to make this are working with. I think it's just, I'll say it's just this like positive partnership that we have, that we will go back and forth, that NASA offers these, objectives, and we say we're doing this, but then there's this reliability. You want to get more reliability, we can offer these extra, but again, like
that's going to cost you.
Of course, right? So like it's, but I think we can work it together and see what's best. One item that came up today during the panel was like the standardization of systems. Let's say we have our lunar lander right now that was launched at 469 kilos of dry mass, right? And we can offer this amount of like mass to the moon. So maybe in the future we work on like, okay, maybe we can repeat this lander without requiring all the development to do it more times equally, right? Without too many iterations, to allow to keep still the price low, and then you can adjust to that. So I think if we could find a way to like standardize more like interfaces, right? To make it's the same thing we do with rockets, right? You don't make a new rocket every time you launch a payload, right? You have a rocket that you launch, and then it just stands there.
This is relatively new though, concept.
It is. So I think on landers it's something similar that we might get to a point that's like, hey, I have always like for this size of payloads, I have this lander that works. For this larger size, I have this lander that works, and I can make not 1 or 2 because it gets expensive. I can make 4, 5, 6, 7, 8, right? Rovers, right? For like Blue Ghost Mission 3, we're gonna have a rover, right? Maybe you're getting into a point that also like it's a rover that's gonna get out of our lander, right? So you can get to a point that you standardize these processes, and we have payloads that can adjust to that specific rover, and then we can, we spend a non-recurring engineering in the beginning, we develop it, but once it works, don't change it too much, right? Put new payloads, but we'd like the infrastructure, like the bus ride to always be the same, right? You put different people on it, but your bus should be always the same.
Right.
That's kind of what we're, but I think it's been working very well.
Well, I wish you the best of luck, and congratulations again for that wonderful landing and the beautiful pictures. I think that were very inspirational to many people.
Thank you very much. We're very excited we were able to be a part of this program, and then this goes all to the Blue Ghost team. That they are the ones who made this possible, who put all the all nights working, all their families working very hard, and at the end, look, it paid off for itself. We have science and images that are mind-blowing. That land is going to be there past our times. It's going to be forever there, so we are very, very happy to have this. So thank you very much for the opportunity.
Yeah. Who knows how long, how you've influenced the kind of coming up generation as well in terms of people that.
Yes, the kids, that's the best. They are so excited. We have so many kids coming here and asking for stuff. We give tours on site. They see the next lander coming up. Yeah. That's the exciting part, right? That we have the new generation coming up. That like I see us like seeing I was not even there on the 60s on all those landings, right? And now we are again there. Last American landing was in 1972, right? And now we landed again, and we show, hey, we can do it. We can do it first with landers, smaller landers. We can get to humans as we're doing with Artemis. Like, it's very, very inspirational. And I'm hoping that all these kids will work hard, and then we'll contribute.
Yeah. No, it's real. So thank you very much.
Thank you very much.
Thanks.
I appreciate it. Thank you.
Hello, thank you very much for joining me today. We're here at the Goddard Space Science Symposium, and I'm with Trent Martin. He's the Senior Vice President of Space Systems at Intuitive Machines.
That's correct.
Thanks for coming.
Thanks, appreciate it.
Introduce us to the recent lunar lander experiment mission that you guys had recently.
Yeah, so on just a few weeks ago, we landed our second mission on the moon. It was our IM-2 mission. We called the spacecraft, which is our Nova-C spacecraft, we called it Athena.
Athena, very nice.
Athena had multiple experiments from different parts of NASA. We had a hopper, which we built internally, and it had science experiments on it that were from various places. We had a drill, the Prime 1 drill, which was a combination of the Trident drill built by Honeybee and the M-Solo mass spectrometer, which was coordinated by NASA Kennedy Space Center. And then we had a rover that was used to test out the Nokia LTE system. And we used not only the rover, but also the hopper to test the Nokia LTE.
Nokia LTE, just for our audience, explain that.
So 4G.
Okay.
Think cell phones, 4G.
Got it. I could have thought Nokia, but
yeah, that's exactly what it is. So the idea was to find a new way to communicate on the moon using cellular, rather than the traditional UHF or S-band radios that we've used in the past. And that way you can get a lot more data bandwidth across your network, essentially create a cellular network on the moon.
Right, so you had a total of 3 NASA experiments on board?
There were 3 NASA experiments, and then we had other experiments on board. So we had the Lone Star experiment, which is a commercial company that's looking to put servers on the surface of the moon. We had Yaoki rover, which was a small little 2-wheeled rover that was going to rove around for several hours. We had Columbia Sportswear. The second time we had Columbia Sportswear on this mission.
Oh, tell me about this partnership. This is really fascinating.
This is a great partnership that we have with Columbia. Columbia was interested in doing something outside of their ordinary, right? They're a sportswear company. But they're actually, we found very, very good scientists. The liner of their jacket is engineered in such a way that it can keep you warm right when it's cold out. We partnered with them, took that liner and tested it on our first mission and then used it again on our second mission. The first mission was just to prove that it worked. The second mission, we actually used it as a thermal barrier for our electronics.
Wow.
And Columbia loved the concept because they got to test in the ways that we usually test in the aerospace world that they don't usually do in the textile world. And they found that they could make their jackets 30% lighter than what they had before. So the same jacket technology keeps you warmer with less weight.
So these are kinds of like more modern partnerships, not the traditional partnerships that you would think where, a government with kind of standard space industry, if you will.
Yeah.
And of course, the byline for the symposium is Pathways and Partnerships for U.S. leadership in space and earth science. So how do you think these kinds of new partnerships might
the key that Commercial Lunar Payload Services is doing is they're trying to find a way that NASA can do missions for less money, right? And only pay for part of the mission. Well, if they're only going to pay for part of the mission, I got to find a way to fund the other part of the mission. So that includes things like partnerships with Columbia. That includes things like selling the Ioki rover or the Lone Star experiment to show that we can bring in commercial companies, we can bring in sponsorships and partnerships to test out new technologies. We can launch ride shares. So we buy the entire Falcon 9, but we didn't use the whole Falcon 9. So we launched 3 ride shares, Astroforge, Epic, and Lunar Trailblazer, which is actually a NASA satellite. We launched those along with us. They went out towards the on the translunar injection, so out towards the moon along with us, but they went separately and they went on their own way and did their own thing.
Right.
And we're able to sell that to help offset the cost of launch. We actually don't like the really long missions that get out to the moon. Here's why. The Earth has the Van Allen belt that has radiation that bombards your electronics. You want to get through that as fast as you can with your electronics off if you can. So for us, it takes us about 4 days to get to the moon.
Okay.
So we launch out. SpaceX gives us a boost that puts us into a translunar injection orbit that's 380,000 kilometers by 185 kilometers. So we go out 380,000 kilometers, and if we turned around and came all the way back to the Earth, we'd only be 185 kilometers from the Earth. We don't do that. We actually fire our own rocket engine and go into orbit around the moon about 4 days after we launch. Then we stay in orbit around the moon for a couple of days, prepare our spacecraft to go land, and then we went and attempted to land.
Okay, now you say attempted to land. I know that I'm sure people are aware that it was not wholly successful. But what happened and what did you learn from that experiment?
So the first mission, by the way, Athena was our IM-2 mission. It launched only a year after our first mission, the IM-1 mission, which we called Odysseus. Odysseus launched and landed on the moon and ended up on its side. And we operated on the surface of the moon for 6 days, and we sent back data from that position on the moon. We did what we call a hot wash after the mission, where we look at every single thing that went right and every single thing that went wrong.
Okay.
And we identified 85 things that went wrong.
Okay.
Right?
On Odysseus.
On Odysseus.
Yeah.
For Athena, we fixed all of those. Every single one of those things that we identified worked.
Right.
We fixed those, and the very next thing that could have hit us again. So we ended up on our side in a crater. We published that picture. So we did actually end up landing in a crater at the south pole of the moon. We were 5 degrees off of the pole, only about 160 kilometers from the south pole of the moon.
That's unique, though, right? To actually be landing at a pole.
Extremely unique. So
right.
No one has landed closer than that. On Odysseus, we landed at 10 degrees from the pole. This time, we landed 5 degrees from the pole. So we're stepping up to landing at the South Pole.
Scientifically, why is it harder?
It's harder because the sun is essentially always on the horizon. So what you're seeing is really long shadows. So even things that don't look like they would give you normal shadows if the sun is overhead, like if you're landing at a mid-latitude,
right?
Like the other mission that landed this month, the sun's overhead, or even if it's coming up and going up above you, you get a lot of sun. You look at their landing site, and it's lit, but well lit. Everything's well lit. In our landing site, some things were well lit. Lots of things were dark. So you get a lot of shading. So that wreaks a little havoc on your landing systems that we use, because we use optical navigation systems. So we're using cameras to look down. We have cameras. We have IMUs, so inertial measurement units, that tells us where we're moving to. So you have one in your cell phone that tells you whether you're moving. And we use star trackers. So we can tell where we're at, we can see what's below us, we can map it relative to a known map based on Lunar Reconnaissance Orbiter. We were able to take maps of the moon and say, we know we're going to be over this track, and that system worked great. It worked perfectly. What didn't work was the laser system. And we don't know why. We're still looking into that. But specifically for the laser, what we're going to do is we're going to bring ESA and the company and NASA with our team. And we're going to go through that very specific system, trying to identify what went right, what went wrong, why did it go wrong? And then separately, more importantly, what are we going to do differently?
Right, because you have another mission coming up in a year.
I got another mission in a year, and then I've got a mission a year after that.
Right,
so
right.
I have to get this right, and I'm going to add some redundancy in places that I didn't have redundancy.
Yeah.
In a traditional aerospace mission, it'll cost you $1 billion to go run a mission like this. You'll have redundancy all over the place, and it's great. We're not doing that. We're doing these missions for $100 million. So you don't put redundancy in places because those lasers are expensive, right? And if you buy 6 of them instead of 2, it's going to cost you, 3 times as much. So you try not to do that if you can avoid it. In our case, we had 2 lasers, so we said we're good. We have some redundancy, but we didn't have redundancy in the right places. So we're going to probably end up with maybe a different laser, maybe this laser operating correctly, and maybe a dissimilar redundant system. So some other technology that allows us to also measure the altitude.
Yes.
It is very important that we have the altitude as we get close to the surface. And that's what got us last time. That's what got us this time. It was for completely different reasons.
Interesting. We've talked about CLPS, the Commercial Lunar Payload Services Program from NASA. What would you like, if you could kind of tell our audience, what do you think the government could do better for supporting this integration of commercial into the future space sector?
Well, I think actually CLPS is a very good example of what the government is doing right? They're literally saying, I have this component, I'd like you to take it to the moon and send me data back in 3 years, right? You figure out how to get it there, you figure out how to launch it, you figure out how to land it, you do all the rest. So one of the things that can be done is, trust your vendors.
Yeah.
Trust that they're going to do what they said they were going to do. And when they say they're going to build something, if they say they're going to do a test, trust that they're going to do the test. You may want to review the test plan,
right?
But don't ask them to write a plan for how they're going to write the plan. You can get a level of oversight that's just a little too much,
right?
And it drives the cost up because just writing that plan took a couple weeks of somebody's time to sit and write a plan, and then we all have to go look at that plan to write a plan. It becomes almost absurd. So I understand the need to have the oversight and the insight, but there's a level of a pendulum that says, I don't trust you at all, to, hey, you guys can do what you say, just tell us how you're going to do it.
Yeah. So helping kind of bring costs down, streamlining the process for commercial,
the key,
building trust.
The key is to build that trust relationship with the vendor to say, yeah, we trust that you're going to do this. And it's probably not a plan for a plan. No.
Well, we'll see. I wish you guys luck on your launch in 1 year at the IM-3 launch, right? October
yes, we have not named that vehicle yet. So we often let our employees name the vehicles. So I'm looking forward to see what we end up with the name for that vehicle. But yeah, I'm looking forward to that. Thank you for the luck.
Well, Trent, thank you very much for joining the Space Policy Show.
All right, thanks.
I'm here with Casey Dreier from Planetary Society, and he is the Chief of Space Policy. Now, thank you for kind of coming out of the conference with me for a moment.
Absolutely.
We're in a back room, but I really appreciate you taking the time to be here.
Anytime.
So can you just introduce the audience to Planetary Society quickly?
Planetary Society is the world's largest independent organization. So anyone in the world can be a member of the Planetary Society, and the vast majority of our members are just regular folks in the public who love space science, exploration, the search for life, the things that really make us feel something really exciting about, our future in space. We were founded by Carl Sagan in 1980, and Bill Nye is our boss right now.
Oh, you got some big names then, too, right? Neil deGrasse Tyson as well as an advisor.
He was on our board, and good friends of the society still.
Excellent. So at the conference here, the Goddard Space Science Symposium, you moderated a panel, and it was kind of about the public science versus private sector, and asking the question, Are these two entities a contradiction or a complement?
Mm-hmm.
What is, as moderator, what did you hear in that panel? What are some takeaways?
For me, it was much more of a positive discussion. Not that I was necessarily negative on it,
But there's a lot of excitement from the scientific community about the possibilities that private providers can give them. And I think the key takeaway, though, is that these are very different types of opportunities than they're used to having. So the classic way of doing space science is that scientists set the question and then work backwards from there. What mission do I need to answer this question? And then what do I need to build this mission, and how do I get the money to do it? And we've got really great results. We have Voyager, Europa Clipper, Cassini, Mars rovers, all that. But those are, relatively expensive. And commercial provides, maybe instead of building one really nice spacecraft, you get to send 10 things, say, to the moon. And maybe some of them will work and some won't. But the number of opportunities is so much larger, and the number of volume of data you can get back is so much greater, that it kind of balances out from that pure question-driven approach into opportunistic science that can still tell us something. So the scientific perspective on that seems to be exciting for them, with a few key adjustments and to make it work better for the scientific community in ways that we've thought about for the commercial community itself.
Interesting. So elaborate a little bit more on the kind of science that commercial might be interested. I know certain, I often hear about how, regulation or standardization, kind of creating an environment of certainty so that commercial has the opportunity to go from, demo to production, to make it scalable, to ease investors, feelings about risk. But what kind of science are you talking about in terms of that, that commercial might be really interested in?
Well, I think the key here is that the commercial perspective is that science will be a customer for them. And at the end of the day, commercial science is almost a misnomer. It's a commercial enabling of scientific activity by a public entity. So everything we've done with CLIPS, that's been NASA paying for. I mean, they've had a few private submissions to it. The vast majority of the money is NASA. It would not exist without NASA money. And the scientific perspective is, okay, we're helping to create these platforms. They can have different types of ways to interface instrumentation onto them. If we standardize that makes it easier for scientists to propose instruments to it, saves a lot of time on their end figuring out how to integrate it into a spacecraft to just focus on the science.
Right.
And then also the idea that if it does crash, maybe the scientists get another shot with their same instrument on the next one. And that's kind of the disparity now.
Right.
We built CLIPS to say any one of these companies, if their spacecraft doesn't make it, they have another opportunity. But the scientific team that built the instruments on that spacecraft that crashed, they don't. And that's the end of their part of that experience.
Yeah.
And so they don't get data, they don't get the funding to keep going, and they have to restart from the beginning. So I think that, to me, was a really interesting discovery we made in this panel, is that can we take this idea of certainty and confidence that we give to this commercial community in order for the reasons you just outlined, and apply that to the scientific community to say, instead of building one of these, build 2 or 3, which is marginally more expensive, but not triple the cost.
Right.
Because you've already done all that upfront
The design
work.
and the demo.
And then if they don't make it, then you have also another shot. And so it's aligning that kind of scientific confidence with the commercial market investor confidence, and you can get a lot more, I think, long-term benefit from these things from both communities.
Right. And so, CLIPS was about payload services for the moon. Do you have ideas about Eclipse 2.0? I mean, would that include Mars? What do you think?
Well, I think Eclipse 2.0 would be maybe a different way of approaching the moon with larger commitments and block buys of some of the discussion we had. And then, we were looking at, can CLIPS apply to Mars? And something that I think is really important also from this discussion is that just the nature of how we approach commercial, these types of rapid iteration, fail fast, try again, multiple shots on goal. Those limitations and the requirements of the investor community, even if you're just serving science as a customer, that means you kind of are limited into what domain of space you're talking about. The moon makes a lot of sense because you can launch every month. You get there in a couple of days to a couple of weeks. Real fast if your mission is not going to work. Mars is probably about as far as you can push it because you only get a launch opportunity every 26 months. It takes 9 months to get there.
As of now.
As of now.
New technology might change.
Well, even if you reduce the travel time, you still probably are still talking about every 2-ish years to launch.
Yeah.
And so your pace of iteration slows down dramatically from monthly to annually or every 2 years. And that just makes it much more difficult. Not impossible, but anything beyond that, launching to Jupiter or to the Mercury, where it's really hard to actually get close to the planet, those probably will never have the same opportunities with commercial space, just because the requirements and the distances and the number of times you can send something there are just so much fewer. And so I think that's where it's like smartly leveraging the understanding of where this model works and where it doesn't make sense to apply it.
Yes.
And really leveraging, again, what are the unique capabilities that the commercial sector can offer in these domains, and then understanding the public sector still has a very important and unique opportunity and responsibility to provide access and science to these harder to reach places. And that, I think, that's a really important distinction, because we can't just say this model will work everywhere. It works somewhere, and it could, and we're still, and as we talked about in the panel, still in the experiment mode. We still don't really know if it will work at the moon. It seems very promising.
We've had a couple of successes. And
we've had one full success, I'd say a partial success, and then 2 failures.
learning moments, not failure.
Right. But, and I hope that gets better. But at the end of the day, I think, will that then continue in the long run? I think it's worth trying this experiment. But again, still an experiment.
Right. And you need that public sector, you need the government to be asking those far-reaching questions, scientific questions, and creating an environment for the foundational investigations, right?
Yeah, there's no commercial benefit. There's no market for knowing if there is life on Europa, right? And that's fine. I mean, that's why we have a public sector, to ask those big questions, to give that, in a sense, intrinsic value of knowledge back to the community, back to the nation, and out to the world. And then buy these services and help the commercial community in ideas that it helps foster this larger set of goals at the moon, maybe at Mars. You start, you're saying, what are our needs as a nation? And so having a healthy commercial space sector is a stated objective of the United States. CLIPS is a way to help with that. Going to Europa, that is a fundamental advancement of human knowledge. That is not a business responsibility. That is a public responsibility.
Yeah, finding the business case. Yeah.
I mean, maybe they'll have, gold. There's just some valuable ore.
Or something even more valuable.
Right. And you're unobtainium. But I mean, that's the sense. Because we don't know what we're going to find, that's why you cannot make a business case. What investor says, what are my returns? I don't know. And it'll cost $2 billion to get there. No one's going to give you money for that. So why do we have a public sector?
Yeah, right.
And then we have where we know things better, then we can apply these other tools to it.
Very good. Well, thank you very much, Casey, for joining the Space Policy Show.
Yeah, I'm delighted to be here.
All right.
You guys, what a great event.
Absolutely. Really well.
Thank you so much for inviting the Space Policy Show here to the Goddard Space Science Symposium. I've already shown it during the show, but I just wanted to show what a lovely. So I'll ask you to introduce yourself, and we're basically just having a kind of closeout discussion on a 3-day event here in Greenbelt, Maryland. So please.
So hi, I'm Jim Way. I'm the Executive Director of the American Astronautical Society.
Well, welcome.
Thank you
very much.
All right. Thank you, Colleen. Ron Birk, serving as the president of the board of the American Astronautical Society, and also with the Aerospace Corporation, leading our Space Enterprise Evolution Directorate.
Yes, and you are also a partner author of the Center for Space Policy and Strategy.
Absolutely. I'm proud to be affiliated.
We're proud to have you. So let me start, Ron, let me start with you. Let's talk about some of the key takeaways of these 3 days.
Oh, absolutely. For a conference that had a theme of pathways and partnerships for U.S. leadership in Earth and space science, it was really, really great to hear all of the discussion about the importance of integration, in particular space enterprise integration. And we were able to benefit from the panel discussions talking about that at very high levels across, for instance, the whole astrophysics community to very detailed levels having to do with specific programs and relationships that were part of the space weather team.
Yeah, I heard things like integration system of systems engineering, integrating multiple kind of players across government, everybody being on the same page, and that being so useful.
Absolutely, and one of the key elements, as you mentioned there, is the integration across the government with the private sector and the commercial sector, and areas where there is seamless integration, where things are working really well, where there's a shared purpose to achieve a national mission goal, and other areas where there are opportunities for improvement. We can get into that.
Challenges.
Yeah, that's right.
So, well, how about you, Jim? What was something key for you this week?
Yeah, I think it's what an opportune time to have all of these discussions. There's obviously a lot going on in government and all in the industry, and to be able to bring all these people together from a really diverse set of organizations and representation in those organizations, I think it's something that AAS strives to do. And hope it provides a valuable contribution to the community to let that happen and have those frank and forward-looking discussions.
Yeah, you guys definitely integrated some great networking breaks throughout the 3 days, and the people. I mean, obviously, we're in a virtual world, and it's good to have the Zoom, but people that were in the room, I saw so many good conversations.
That's a big part of it too, absolutely, is to bring people together, not only to hear from industry leadership, but also just to talk with one another. And again, it's a very diverse and wide-ranging set of attendees, ranging from CEOs and heads of government agencies to new entrants to the workforce, and plenty of students. And we're so happy to have the students here.
Yeah, they bring so much energy and real insight, actually.
Right.
Students.
Yeah.
And they're not hesitant to ask some very interesting questions as well. So we love that too.
Well, fresh eyes for sure. And that was actually one of the kind of challenges that I heard a couple of speakers talk about, or panelists talk about, was the challenge of workforce for the future, and the fact that you guys are kind of leaning into that. And many organizations are trying to lean into it, right? But times are hard right now. So what about some other challenges? I mean, I wrote down some, like in terms of the moon, right? Kind of technical challenges of transportation, dust, power, some other challenges besides people and workforce, budget overruns. My personal favorite that I heard throughout the week was messaging, in terms of how civil space can change its message in these times of budget uncertainty, economic uncertainty, the rise of geopolitical tensions, and how civil space feeds into those aspects. But what are some, Ron, can I start with you, some other challenges that you kind of saw in terms of this week?
Absolutely. So one of the key challenges that we're seeing is this evolution from our legacy of a relatively smaller number of major organizations building purpose-built space systems. And of course, we have many examples of that up to and including the James Webb Space Telescope, which is absolutely phenomenal. But we're seeing this transition over time to a larger number of commercial and international organizations that are joining in with U.S. government organizations in developing space systems. And so the more of these capabilities that are developed and deployed, the more we are evolving into a space ecosystem environment. That brings up the challenges of integration within those different organizations, and also the need for essentially doing do no harm analysis to make sure that the capabilities that one organization brings into space is not interfering in an unexpected or unintended way with the capabilities that others have.
And there are also a couple of great discussions on the policy surrounding all of this. The what's in place now, is that prohibiting certain things from taking place, and what can we do to enable a lot of this to happen? And so there are a couple of fantastic discussions on that. Yeah.
Can you give me some insight on a potential CLIPS 2.0, the Commercial Landing Payload Services 2.0? Because the first 2 days, the first 2 days had a lot of exciting insight from commercial players, and we here on the show, on this particular episode, we talked to both Firefly and Intuitive Machines, and so that kind of commercial lunar presence. But are there lessons learned that could happen next?
Well, I think part of it, like you said before, is communications and awareness about all of this, and I think having a broader public know about these missions and what they're capable of doing and what might be next is important for them to understand the value of these things, and also to get new entrants into this field and have them start to play in this environment as well. And it also goes to show that it's not an easy thing to do. And so, we've seen that, and for them to rise to the challenge and to have the success that we're seeing, it's amazing.
Yeah.
It's amazing.
Yeah, two really high value ideas that came out of the discussions. One was the idea of standardizing the interfaces on the different CLIPS missions so that it was possible to plug and play, as the expression goes, instruments into different CLIPS landers and providers. Another real high value approach is under the auspices of a block buy. The concept
of a block
buy, like buying in bulk. The efficiencies that come with buying, with the government actually buying several landings as a package, so that there is a larger set of activities to amortize the non-recurring engineering costs over, but also so that the community that is seeking the opportunity to use these landers, right, science and other purposes, would have more opportunities to be able to deploy their instruments and other payloads.
Yeah. That's kind of going into what I wanted to talk about next, was in terms of what you're hearing from industry, right? So that, I heard about the onesies, twosies are not profitable,
and not
right?
sustainable.
Like how to get to that demonstration and to that production for commercial. In terms of sharing and integration, I mean, what can we look at for intellectual property, for international standards, maybe relooking at FAR again, sharing of people. One of the things that I heard that struck me was the idea of perception, a perception problem as we tout all these great successes of commercial space companies, whether it's SpaceX or Firefly or Intuitive Machines. Are we then diminishing and sacrificing the role that government has played in these endeavors?
And needs to continue to play.
Right.
It's a really important element. So as many of the panelists and speakers highlighted, there is a really foundational role for the government to develop fundamental technology, to deploy it, and to do so in a way that the community across the board, across the enterprise, is really cognizant of how it was done, and that they have the benefit of the government has the benefit of providing data and information that has the element of authoritative source of truth, right? So that people can trust in what they're seeing. This is very true for earth science. It's equally true for space weather, and it extends out beyond.
Yeah, and I heard from industry something about what you're talking about in terms of that trust, is that when government provides opportunities for science missions, those science missions need to integrate some sort of technology demonstration or technology proof, so that then the private companies can take that elsewhere and kind of move around with it.
And that turns out to be extremely valuable, both for confidence, not only in investors, of course, right, but insurers and regulators are also very interested in understanding the confidence that they can have in the systems. Many times that's talked about in terms of risk, right? But there is a very important element of building confidence in these systems.
Yeah. Let the government do the super hard stuff, the novel things, and prove it out.
And set the stage, set the foundation.
Yes. What did you hear from industry?
I think they're very excited about all these opportunities that are coming. I mean, they're getting much more. They're getting much more buy-in and much more play in all of these endeavors, and I think they're very excited about it. But they also see the challenges. They have to prove it. They have to prove their worth, prove their value, ROI and things like that, and that's going to be challenging for sure going forward for them. And we'll need the government to keep going, to keep helping enable that, both from, like you said, the truths and also the policy, the regulations, everything. So that's what I'm hearing from them.
Yeah, thank you guys very much again for appearing on the show today.
Thank you.
And I look forward to seeing you again next year at the
Indeed.
symposium.
Absolutely. Thanks for seeing us.
My name is Abigail Fichet. My name is Niharika Naveen. I'm a junior at the University of Illinois at Urbana-Champaign.
I'm Takumu Hamanaka.
My name is Nicolas Monayos. I'm going to the University of Illinois with Urbana-Champaign.
My name is Arushi Sharma.
Hi, I'm Axel Wieck. I go to Purdue University. Yeah, I think one of the big problems I'd like to tackle in space science is on the propulsion end of things. I would love to tackle advanced electric propulsion systems and the novel new types of spacecraft design that involve them, whether that's the new power systems, the new payloads, and in order to enable more ambitious exploration of the outer planets and beyond.
The biggest challenge I would want to tackle is advancing biomedical research for human spaceflight. There's not much research that exists. I would think back to maybe like the NASA twin study or the time that they printed 3D printed human heart tissue in 2019. But other than that, there hasn't been much major research. So especially as we are advancing human spaceflight, there needs to be much more biomedical research done for our astronauts. I think the biggest challenge that we need to tackle as a scientific community is the collaboration between every sector of aerospace. So that includes the private sector, the public sector, academia, students, because I think collaboration on a global scale is imperative to advance the next generation of spacecrafts and satellites.
I think a big challenge that we need to solve, or would be really great to solve, is improving on precision landing systems for both unmanned and manned landers, so that when we send supplies and crew to the moon or Mars or wherever, we can land where we want, not where we can.
I would like to improve our ability to send larger and heavier payloads to low Earth orbit and beyond.
The biggest challenge that I think we need to tackle is bridging the gap between the technical science and engineering communities and the general public in understanding that science in space is extremely important in innovation, and innovation that people use in their everyday lives.
I love the enthusiasm and thoughtfulness of today's future space workers. I hope they continue asking the hard questions and striving to make us better. The government science also asks hard questions, and by offering opportunities to prove out key technologies and scalable solutions in science missions, government could help tee up commercial space for success. As one panelist put it, space is a baton race. So all of our shows are available on YouTube or wherever you get podcasts. You can follow us on LinkedIn to get notified or even engage with our speakers. Thank you to James Liggins, our technical director, and thank you to our audience for watching or listening.